Hello guys, today I will teach you how to approach and solve dynamic programming problems. Unfortunately or fortunately, dynamic programming problems show up everywhere, either in programming competitions or in job interviews. So my main focus today would be on giving you some tips on how to solve a dynamic programming problem that you haven't seen before. First, I will review what dynamic programming is. Then we will solve some example problems, starting from easier ones, moving on to more complicated ones. And then as we solve them, I will provide you with some tips and techniques so that you know exactly what to do once you see a dynamic programming problem for the first time. So let's get started. At the heart of dynamic programming, there's this concept called memoization, also known as caching, also known as using a lookup table, which basically all it is to remember the result. So if you have a function that takes an input and performs a very complex calculations on that input, when you receive the same input over and over again, rather than doing recalculation, you can use a memo. Basically, you use a memory location. It can be a map or a vector or an array. And then we first check to see if the answer is in the memo. In that case, we return the memo value. Otherwise, you create the memo location and return. So we first check to see if the answer is in the memo. In this case, we are done. We return the value. Otherwise, and only then do we perform the complex calculation and then return the value. So for example, if my input sequence is 1, 2, 1, 100, 2, 1, and so forth, then for all the cases that I see the same input that I saw previously, for example, for 1, for 2, I've seen it here, and then 100, I've seen it here. For those cases, I can save runtime. Now let's look at Fibonacci numbers. Basically, you define it as fib of n is equal to fib of n minus 2 plus fib of n minus 1. And your base cases are 0 and 1, for which our output is 1. The Fibonacci sequence is like this. If we want to calculate fib of 5, for example, you have to calculate n minus 2 and minus 1, which is 3 and 4. And then for f of 3, you have to calculate f of 1 and 2. For 2, you have to calculate f of 1 and 0. For 4, we have to calculate f of 2, f of 3, and then f of 1 and 0. And then for 3, we have to calculate f of 1, f of 2, f of 1, and f of 0. These are a lot of function calls, but now using memoization, you can see that because we calculated f of 2 previously, we don't have to recalculate it here. And because we calculated f of 3 previously here, we don't have to recalculate it here. That means using memoization, we are being saved from exploring these two tree branches. This has a rather complicated name, but again, don't be scared of this name, which is overlapping subproblems. All it is that if you can break a problem into multiple subproblems, and then you observe that these subproblems are the same or they overlap, which we saw here, for example, a subproblem of f of 2 under f of 4 was overlapping, or it was the same as f of 2 under f of 3. So this is a very important feature that a problem needs to have in order for us to be able to use dynamic programming technique. Now, loosely, we can say dynamic programming is really using a recursive function plus memoization. Here is our Fibonacci function implementation, our base case, n minus 1, n minus 2. And then if you want to add memoization, again, you can add a map. You could also use a vector or an array. And after checking for base cases, you check to see if the result exists in the memo. In that case, you're done. You return that value. Otherwise, and only then do we perform the calculation. And then we update the memo. Now, this, if you measure the amount of times that we recalculate values for example, fib of 30, this picture shows that if we are calculating Fibonacci number, the 30th one, you will recalculate, for example, f of 2 over 500,000 of times. Now for f of 6, that comes down to about 85,000, which is still a lot. And even like around f of 16, you still have about 500 recalculations. But if we use memoization, we only would call f of values less than 28, less than or equal 28, only twice. Now that means we can save a lot using memoization. So from over 500,000 of times, we come somewhere around 2 or 1. So this becomes a constant. Let's look at Fibonacci and the way we calculate it one more time. So we are calculating fib of n. We break it into two subproblems, f of n minus 2 and fib of n minus 1. And then we run a function on these two subproblems, namely addition, and then we get the result. Now this breaking into subproblems and running a function on the result of these subproblems has another complicated name, optimal substructure, which is basically what we just said, breaking a problem into multiple pieces and then solve these pieces optimally and then run a function on their results to get the optimal result to the original problem. So now again, loosely we can say dynamic programming is a recursive function plus memoization where we have optimal substructure and overlapping subproblems. These two features are inherent for a problem that we want to solve using dynamic programming. We saw how we use the memo and then we filled it up. There's another technique, or I should say there's another way of filling up the memo, which is called tabulation. So for Fibonacci, again, we started in our first implementation to say fib of n is equal to fib of n minus 2 plus fib of n minus 1, and we kind of moved from top to bottom or right to left. And that's what in literature is usually called memoization or top to bottom. Now, if you fill out your memo from left to right, you're still doing memoization, but the name for that in literature is usually tabulation or bottom up. So we could go either this direction or that direction. They're the same thing. It's just the sequence of calculating these functions. Now, the tabulation implementation of Fibonacci, usually when you go tabulation, you use an array or a vector, and then you start from the bottom, and then you fill out your locations of this table, and then you return the last item as your result. Compare this to memoization, which we go from top to bottom, where we, for calculating f of n, we go to f of n minus 1 and n minus 2, and then we use a memo to prevent recalculation. Now, what do we need to know about tabulation? So your memo in memoization, it can be a map or a vector, but in tabulation, usually people use just a vector. Now, one thing that you have to be careful about is the indices and allocation of this vector. For example, here we use n plus 1 locations. The runtime is similar to memoization, and then often this memo or this table can be optimized. For example, here, when we are calculating each new location, we only need the last two ones. So we only need n minus 1 and n minus 2. So that means this huge table, which is of size O of n, can really be reduced to only two locations. Now, implementing Fibonacci using only two locations, I leave it as a homework assignment for you guys, but it's basically what we just said, and it shouldn't be too hard. What do we know so far? Dynamic programming is avoiding recalculations for recursive functions. We can use either memoization or tabulation. And that's all it is. That's basically all you need to know about dynamic programming, except that finding out this recursive function is not usually easy. So using memoization or tabulation usually is not too hard. Everybody can do this. But coming up with this recursive function, finding out that this problem has the inherent two features that we talked about before, the overlapping subproblems and optimal substructure. So understanding that part and coming up with this recursive function is usually the hardest part. And my job today is to giving you guys some techniques on how to solve dynamic programming problems and how to basically come up with this recursive function. All right, let's see this in some examples. Example 1, a famous problem called coin changing problem. So you are given different coins and a total amount, and then you want to find out the minimum number of coins to make up to that amount. For example, you have an array of coins of $1, $2, and $5, and you want to build up $11. What is the minimum number of coins that you need to get to $11? And the optimal answer is 3, which you can build 5 plus 5 plus 1 to get to 11. And there's no other combination that has less than 3 coins. And remember that we can have infinite number of each coin. The first thing that you need to do for any dynamic programming problem is to propose a cost function, which really requires a lot of thinking. Let's go back to our example again. After a lot of thinking, you might come up with a suggestion that says, let f of I be the minimum value to get to the total amount of I. So there's really not a general way on how to come up with this function, but what you can do, and usually it works, is to look at your input parameters and see if you can use any of those for the parameter of your cost function. So in this case, for example, we tried the amount f of I, and then what you really want with this definition is f of 11. So with this definition, the next step that you need to do is performing a case analysis, or basically find out how you can come from an f of a value which is less than I and do this leap, do this jump, and get to f of I. Let's get back to the problem. So we want to write the value of f of I for values less than I. In order to do this, usually what really works is case analysis. Basically, we want to find out all the cases that helped us to get to f of I. In this case, for example, if you really think, you can see like at the last moment that you take this jump to get to f of I, what happens is that you have to pick either of these coins, either coin 1 or 2 or 5. That is the basis of our case analysis. If you pick 1, that is case 1, then you can write f of I is really equal to f of I minus 1. 1 is the value of the coin, plus 1 because we just picked a new coin, namely coin of $1. The other case is that we pick 2. If we pick coin 2, then f of I would be f of I minus 2. 2 is the value of coin 2, and then we add plus 1 because we just picked a new coin. And then you guessed it, the last case is picking coin 5, and then you write f of I is equal to f of I minus 5 plus 1. But because we are trying to minimize this function, what you really need out of all these cases is to find the minimum. So this is the function that we run on all these subproblems to get to the solution of the original problem. In general, I can write my coins is an array of C0 to Cn minus 1, and I want to build up amount of m. So I can do a case analysis on all the coins. So I will write f of I is equal to f of I minus each of these coins plus 1, and then I find the minimum value among them. And then my base case is very simple. In order to get to amount of 0, I will only need 0 coins. The implementation, the recursive implementation, we're still not doing dynamic programming, is really the direct translation of this formula. So we just check for our base cases, and then we do the case analysis. We find the minimum value, and then we return the value. There's some details here where we want to return minus 1 if we were not able to build up that amount, if the problem was impossible. Now let's look at the overlapping subproblems feature for this coin changing problem. So imagine this other example that I have coins of value 2 and 4, and I want to build amount of 100. In order to get to 100, I can either pick coin 2 or 4. If I pick coin 2, I have to come from f of 98. Again, if I pick coin 2, I have to come from f of 96. And then as you build this tree, you will see that again, we have some overlapping subproblems. For example, here 94 and 94 are overlapping. So, or 96 and 96 are overlapping. So again, using memoization, you are able to completely bypass exploring this huge subtree. Going back to our friend memoization, we modify our recursive implementation. We just add a memo, as I mentioned before. Check the memo first. If it exists, we're done. Otherwise, and only then do the hard calculation. And then at the end, update the memo first and then return the value. Now, tabulation is the reverse direction. We start from the bottom and go to the top, and then basically this is calculating the minimum case analysis. I have a link in the description for you guys if you want to download the code in C++ and play with it. Download it from my GitHub. Let's look at another example. There's another famous problem called 0-1 knapsack problem. So the setup of the problem is that you have a backpack or a knapsack, and it has a maximum capacity of 15 kilograms, for example. And then you have a set of objects. Each object has some weight and some value. Your goal is to pick as many items as you can so that the value is maximized, but the total weight is less than your capacity. So if you want to write this formally, you have a vector of weights, a vector of values representing item I represents object I, and then you want to maximize the sum, which is vi xi, and wi, the sum of wi xi has to be less than your capacity. Xi is either 0 and 1, where 0 represents the item is not included and 1 represents the item is included. Let's look at this example. So your values are 1, 2, 2, 4, and 10, and then your weights are as follows. And then your maximum capacity is 15. Now, if you solve this, you will see the maximum optimal value would be 15, which is when you pick item 0, item 1, item 2, and item 4. And then the total weight would be 8, which is less than 15. How do we solve this in general case? Again, as I mentioned, the first step of any dynamic programming problem, propose a cost function. Now again, a very common proposal or suggestion usually is playing with your inputs. So in this case, we have two arrays, and then usually using the index of this array can work. So basically, we can define a function and say f of I is the maximum sum of values of items 0 to I. Basically, that means if I include items 0 to I, what would be the maximum sum of values? Now, this was step 1. Step 2 is to do case analysis. Unfortunately, if you do step 2, you will see that this cost function doesn't work. Which brings me to the next step, which is trial and error. That means you have to go back to step 1 and just propose another cost function. That requires a lot of thinking as well, but really, all we're doing is just playing with the parameters of this function, usually bringing it from the inputs, either the index of the arrays or other parameters like W that are given to us to do this trial and error. So you really have somewhere to start from. All right, going back to the problem, let's propose a new cost function, which is now we added a second parameter, which is W. That means f of I and W represents the maximum sum of value of items 0 to I with the maximum capacity of W. And then in order to solve the problem, we have to find f of N and W. Now that we have this, let's perform our case analysis. Again, we want to find out how we can get from values less than I and W and perform this jump to get to I and W. And again, case analysis is your friend. Remember that f of I and W represents that you can include items 0 to I such that total weight sum is less than or equal W. So we want to find out what happens when we include item I. Now there's a case analysis. We either include item I, in which case f of I and W is really equal to, because we included item I, we have to add its value. Now your I becomes I minus 1 because previously I was not included, and then your W becomes W minus WI. The other case is that we look at item I and we decide item I is not included. In that case, f of I and W is really equal to the case that we never included item I and we only included items from 0 to I minus 1. Because we are trying to maximize f of I and W, we have to run a maximum function on these two values. So basically, f of I and W in general case is the maximum of the two cases that we just talked about here. And then you have two base cases for when W is equal to 0 and I is equal to minus 1, which basically means you cannot use any of the items. Using this, we can now write a recursive implementation, which is basically the translation of our recursive case analysis. So this is our base cases, and this is our case analysis. And there's this special case for when we know WI is greater than W, which in this case, we know we are definitely picking this case because if WI is greater than W, we know that item I is definitely not included. We don't have to take the maximum. So this is a direct translation. Memoization, as we have seen it many times so far, is exactly the same approach. Check your base cases, check the memo. If it existed there, we're done. Otherwise, and only then, we perform our hard calculations, and then we update the memo and return the value, both in this case and in this case. Tabulation is starting from the bottom to top. So now we have a two-dimensional array or vector in this case, and then we start from bottom 0 for I and 0 for W. There are some details. Again, anytime that you go with tabulation, you have to be careful about your indices and also your allocations. So these are some details. I will leave it up to you guys to, as a homework assignment, to understand it. There's really nothing very special here. All right, let's look at example 3, which is called largest sum contiguous subarray, or LSCS. Given is an array of integers, and we want to find a continuous or contiguous subarray with the largest sum and return that value. For example, if this is our array, this is one subarray. If we sum them up all together, the value would be minus 4. Here is another one. If you sum up all these values, you get to plus 2. And here's another one, which is 4 minus 1, 2, and 1. If you add up them together, you get to value 6. And it happens that this subarray has the largest sum. And this is what we want to find. And as you can see, there is a lot of subarrays here. The task here is to use dynamic programming to find out what the problem is. What is our first step? Don't get scared. Propose a cost function. So let's look at the problem again. As we have seen before, using the index of the array is a good start. So let's pick a function called LSCS, LSCS of I, be the largest sum of a subarray ending at index I. For example, at this location of the array, LSCS would be maximized. Next step is case analysis. How do we jump from values less than I to value I? Now let's perform our case analysis. If you look at location I, input I, is either the start of a new subarray by itself or is part of the previous subarray. And these are all two cases that we are going to analyze. Now, if input I is part of the previous subarray. That means SCS of I, because it's part of the previous subarray, it has to be SCS of I minus 1 plus input of I, so that together they build up a new sum. If it is, on the other hand, by itself creating a new subarray, then the sum starts from this value and it should be the value of input I. And then because we are maximizing this, we have to find the maximum. Now let's see this in an example. In this array, for example, let's look at this value 1. So we have to decide if it's case 1 or case 2. If it's case 1, that means 1 is part of the previous subarray. In that case, the sum would be 1 minus 2, which is minus 1. But if it starts its own subarray, then the value of the sum at this location would be 1. Now we find the maximum and we see it's 1, so then we decide this should start a new subarray. But for minus 3, if it starts a subarray by itself, the value would be minus 3. But if we included in the previous one, 1 minus 3 would be minus 2, and then the maximum between minus 2 and minus 3 is minus 2, so that means it has to be part of the previous subarray. So we can write our recursive function to be the maximum of these two cases. Alright, so now that we wrote this, then we can calculate SCS for every location, and then we see that based on the cases that we chose, there are the subarrays created at these locations, and the value of 6 at this location is the largest. So there it comes, yet another step to decide where we should pick the subarray. So in this case, because this is a maximum, we have to choose this location. That means a subarray ends at 6. And the way to find it is to look at every location in this array and find the maximum. So we first calculated SCS for every location, and then we took another step, which was finding the largest one, which was the maximum. So that brings me to this point that sometimes dynamic programming gives you result to a subproblem like this, but then you have to take yet another step to find the maximum among all the optimal problems. The implementation of this problem is very straightforward. The recursive one is the direct translation of this. So we first calculate SCS, and then LSCS basically finds the maximum among all SCSs. Memoization is just like before. I'm not going through the details. We have seen the technique several times so far. And then tabulation, again, is very straightforward. Before I let you go, let's do one last example, and I promise this is the last one. And this one is, again, another famous problem called the longest palindromic subsequence, or LPS for short. The setup of this problem is that you're given a string. String can be represented in an array. Find the length of the longest palindromic subsequence in it. And remember, subsequence is different than a subarray, which means basically items that come one after the other, but some of the items in the middle might be missing. Let's see an example. For example, in this case, if you take A, B, B, and A, this would be a palindrome. That means if you read it from left and right, it will read the same. This is not a subarray, but it is a subsequence because A came before B, B came before this B, and then all of them came before A. Now, what do we do? Again, without any hesitation, you know the first step, propose a cost function. And I mentioned before, using the index of this array usually is a good start. So how about we use LPSS of I and then say I is the index of the input string. Unfortunately, if you take step 2, which is your case analysis, you will realize that you cannot really write LPSS of I based on values less than I. Which then brings me to this technique again, which is trial and error. We basically propose yet another cost function. So now, how about we add another index and basically say LPSS has two indices, I and j. I is less than or equal j. And basically, this represents a subarray of the original array. So now, for example, I can write LPSS of 4 and 5 from index 4 to 5 is 2. LPSS of 3 to 6 is still 2 because I only have a subsequence of length 2. If I go from 2 to 7, it's still 2. But if I go from 1 to 8, then the value would be 4 because it includes the subsequence of A, B, B, A. So finding out that this is the real cost function, it really came from the palindrome nature where you have to go from both sides to find out if something is a palindrome. What is the next step? You guessed it right, case analysis. So we want to find out how we can get to LPSS of I and j from values less than I and j. Let's do our case analysis. So basically, if you look at a string and I and j, there are two cases. Either these two are equal or they are not equal. So for example, here I have two A's and here I have A and Z. For the first case where the two are equal, then you can say LPSS of I and j is really equal to this part, which is I plus 1 to j minus 1. So LPSS of I plus 1 to j minus 1 plus the 2 that we just added. But if they're not equal, then LPSS of I to j, it's either the optimal value of this part or this part. So one is I plus 1 and j, the other one is I to j minus 1. In this example, we see that it was from I to j minus 1. And again, because we are maximizing, we have to find a max here and then a max between these two cases. And that's all it is to this problem. Once you have this case analysis, you come up with your base cases, which are very simple. When I and j are equal, then your value, the length of the palindrome subsequence is 1. If they are equal and j is exactly after I, then the value should be only 2. And then these are the two cases that we just saw. The recursive implementation, again, is the direct translation of this relationship. And then we add memo to it. Again, we have seen it many times. Check the memo first. If it exists, we are done. Otherwise, and only then do we go back and perform the hard calculations. And then the tabulation for this problem is a little bit different because the order of how you have to fill out these memory locations is a little bit different. So usually you might think that you can start from I and j and have two for loops and you're done. But what you really need is to define a length of all the subsequences and then iterate that length from 0 to size of your input. Once you have the length, then iterate all the subarrays that have this length. You can start from index 0 and then iterate I to where I plus the size is less than size of the original array. And then j is I plus L. Once you have this set up, then you can write down the recursive relationship and case analysis. So this is an example that shows the tabulation requires some more effort to find out how you need to fill out your table. If you blindly go from I0 and then J0, it wouldn't work. What should we take away from all of what I said? First, when can we apply dynamic programming? So as I mentioned before, dynamic programming has two very important features. It needs to have optimal substructure and overlapping subproblems. Once you see these two exist, then you add memo or caching, either top to bottom or bottom to top, and there you go, you have a dynamic programming solution. Dynamic programming is really avoiding recalculation for recursive functions. You can use either memoization or tabulation. How do we solve dynamic programming problems? How do we approach them? Step 1, propose a cost function. In order to start trying different cost functions, look at your inputs. What are the inputs to the problem? Those are usually very good candidates for parameters of your cost function, or the index of the input arrays. This is another candidate for your cost function. So you have a point to start from. Once you choose a cost function, you perform your case analysis. Hopefully it works. But if it didn't, you go and do trial and error and try another cost function. Now, if your problem has just very limited number of inputs, you don't really have to go too many times, and then hopefully you can find it. In order to be able to solve dynamic programming problems, you have to practice, practice, and practice. You basically need to have seen a lot of famous examples and be able to solve some famous problems that I can name off. So some of them we see in this lecture: Fibonacci, coin change, knapsack, minimum, contiguous, Subarray, Bellman-Ford, Floyd-Warshall. Thank you very much, guys, for watching my video. I hope it has given you some ideas on where to start from when you see a new dynamic programming problem. Please click on the like button and subscribe to my channel to see my future lectures. Thank you.